Okay, on to question 4. So this is a signal, and here we're doing analog to digital conversion. So we received this following ASK signal and answer the following questions. So assuming the original signal had a maximum frequency of 3 megahertz, what sampling frequency must be exceeded when sampling the original signal in order to ensure accurate reconstruction from its samples? So usually when we say like exceeding the sampling rate, we're looking for the Nyquist rate, right? And that is Fn is greater than 2 times f max of the signal that we're sampling, right? So f max here is given to be 3 megahertz, so Fn must be greater than 2 times 3 megahertz, which is 6 megahertz, right? So that's all we need to do there. Usually you see the word like exceeded, or if we're trying to calculate some value that we need to sample at to be accurate or to avoid aliasing, that's the Nyquist rate. So those are sort of the keywords that you want to think about to decide when we need to pull that out. It says we end up undersampling the ASK signal by using a sampling frequency of 2 megahertz. What is the sampling period you are using? So as usual, t equals 1 over f, right? The period equals 1 over f. So that is equal to 1 over 2 times 10 to the negative 6th. That's our megahertz here. And so that should give us 0.5 microseconds is what it comes out to, right? So that's our 10 to the negative 6th for seconds, right, is microseconds. So that's what we should end up with. So then it says draw your sample points starting at 0 microseconds on the graph above. So we're going to start there, and drawing sample points, we're just literally find where the signal is and make a sample point there, right? So at 0 and then at 0.5 microseconds, because that's our sample rate, we're just going to draw a circle for where the signal is. It's a little bit hard to tell, but again, like as long as you're doing something reasonable here for where you think that signal is at that point in time, you should get credit. No promises for how nice your instructor is, but should be reasonable, right? So something like this and this and this, and then we're just going to continue doing this for every single point on the graph. Again, we are undersampling as it told us in the question, and so we don't necessarily need to like do this. We don't need to do this like when the signal is changing, right? We can tell that there's stuff happening in between that we're missing, but we were told to sample at 0.5 microseconds, so we're just going to every 0.5 microseconds make a sample point and draw a circle there. So that's it for part B. Part C, assuming the voltage of the original analog signal is negative 8 volts to 8 volts, as shown on the graph, what's the quantization resolution of the ADC? Remembering that it's a 2-bit quantizer. So here we're using the equation Q equals V max minus V min over 2 to the n, where n is the number of bits. So then we're going to plug in our max voltage, 8 volts minus negative 8 volts, over 2 to the n, 2 squared, which is the 2 bits. That's where I'm getting that 2n from. And so that gives us, we have 16 volts over 4. And so our resolution is going to be 4 volts. So we can see the difference between 4 volts values in this chart effectively. So then D, draw your quantization levels and encoding used for the 2-bit quantizer in the graph above between negative 8 volts and 8 volts. So we're going to start off, usually the best way to do this is we've got negative 8 volts to 8 volts. So a 1-bit quantizer is going to draw a line across at 0, right? So that would give us below that is a 0, above that's a 1. To make this into 2 bits, we're going to draw a line in between each of those quantiles, right? So we're just going to divide them in half again. And that gets us now 1, 2, 3, 4 different values. And those are going to be 0, 0, 0, 1. We're just counting up in binary, 1, 1, right? So this is 0, 1, 2, 3 in binary in 2 bits, right? So since it's at a 2-bit quantizer, we're dividing the graph up such that we can get those different values. And so that's what we've got there. And then for the last part, what is the output of the ADC based on the signal above? So for that, we're just going to look at each sample point and we're going to see what quantile is it in, right? So this one falls into it's above 4 volts, so it's 1, 1. This one's in the middle here, so it's going to be a 1, 0. This one's also in the middle here, so it's going to be a 1, 0. This one's above, so it's a 1, 1. Above again, so 1, 1. and then another 1, 0 at the end. And then we're just going to write those values down at the bottom here, left to right. So we should end up with, and I think I took one more sample point than what the exam online solution says, but you would have, these values, just writing them left to right on the graph. And that's, again, just finding out which quantile it's in when we took a sample. Again, we're not dealing with like what happens when it crosses the lines here. I know there's information being lost, but that's part of the point of analog to digital conversion is we have these infinite valued, very fast analog signals, and we're trying to make it manageable for a computer system with digital values. So then part F gets into that, which is what's the effect of undersampling the signal in the received data, and that's aliasing. And the idea here is because we're sampling at the Nyquist rate, if we reconstruct this signal, it's going to look something like this, where we have sort of the middle value of each of these. And obviously, we're losing tons of information about what that signal looks like, right? We're losing all of this stuff that goes below the 0 line on the graph, right? So everything below 0 volts has been lost because we're sampling too infrequently for this. That's it for that question.